All right. Well, we're going to go ahead and get started with lab today. We're going to cover labs 10 and 11 today. You shouldn't be too scared about that, though. They're pretty straightforward. So this week we're going to do lab 10, which is finite element analysis for assemblies. And lab 11 is mass properties. So we're going to go ahead and get started with the mass properties first, since that one's very straightforward. On TCC, I've uploaded an assembly with a wheel rim and a shaft. So if you guys want to start downloading that, we can do that together as part of the in-class assignment. But I'll go ahead and pull up both of the labs real quick here. We can kind of go over the different requirements, what's going to be turned in, and things like that. Okay, so there's lab 11 and lab 10. Okay, so for lab 11, this is going to teach you guys how to learn how to use the mass properties as a tool for improving parts and assemblies. So for this one, we're going to go over an assembly that I've created. It looks slightly different from this. But we'll assign some materials and then do a basic mass property analysis. And then you guys can change the parametrics of that model to kind of see where things will change. And then what you'll do is you'll turn in a Google document entitled lab11_your name with the images from number 1, number 2, and number 3. So these ones will be the assemblies from lab 4 that you'll do a mass properties analysis on. And it's very straightforward, so it shouldn't be too difficult. As far as the homework, you'll use those mass properties and you'll begin to make improvements to your semester project by reducing the weight, moving the center of gravity, etc. You'll apply mass properties to the parts that you've been working on. You'll enter and compare these values to actual measured values gathered from lab 3. So real quick, we'll go ahead and hop into Catia, and I'll show you guys how to do that. So inside of Catia, I've created a wheel with a shaft in it. This is what I've uploaded to Team Center Community, and so you guys can download that if you'd like to.
Where is it uploaded to?
Yeah, it's in Lab 10, and then inside of Lab 10 there's a folder called Catia, and inside of Catia there should be a product and 2 parts. So you guys can download those and pull them up, and I will show you how to do the mass properties on that. Okay.
So we're doing the mass properties of the lab.
Yes.
Files.
Yep. Okay. We're going to be using this one for lab 10, but I figure we can do portions of lab 11, and then I can actually pull up the assembly from lab 4, which we can do to complete the in-class exercise. Okay, so the mass property analysis is fairly straightforward. If you're clicked on a single part and you go up to edit, there is a properties option. And so if you click on that, it will bring up a dialog, and if you click on the mechanical tab, there is a list of everything on the part as far as its inertia, its surface area, its mass properties, its volume, the inertia center. So this is basically the whole lab right there. You guys are going to pull up this information, and then you will check and see what the volume is as well as the surface area. And then you'll be able to go in and look at your topology optimized parts, do a mass properties dialog box on that, and compare the two and see what your weight savings was. So it's a very helpful tool. So when you do that, just take a screenshot of that, and then you will paste that into the Google document. And that will be basically finish the requirement. If you go into the product, you can do the same thing, and it will give you the characteristics of the assembly. So you guys can check to see where the center of the inertia center is, the center of mass, where the mass is, the volume, how much surface area it has, and then all of the different inertias in the different directions.
Are these values that we can change, or they just...
Those are the values that are printed out. And so as you change the model, you guys can see that the numbers will change as well.
And that's going to be based on the material that we applied?
Yeah, based on the material, based on how much volume there is, things like that. And so as you guys are optimizing your parts using topology, maybe you'll do like an FEA analysis and you'll find that there's some areas that need more material. You can add more material, run this mass properties analysis, and see, how much mass you've added. Maybe if you change the material, you can see how much you can reduce the weight. Things like that. So this is a great tool to help you guys do some real engineering as far as, calculating what the efficiencies are, how you've bettered the different parts and things like that.
Next Tuesday, we'll actually lecture on mass properties and the mathematics behind it. But if you just think about if you were the designer of the hood of a car and the structural part that goes under the hood, the webbing that goes under there, what you want to do is try and move the center of gravity of that hood as far back towards the springs as you possibly can to make it so that it's lighter to lift up. And so that's why lots of hoods are kind of tapered towards the front, is to be able to shift that back. And so mass properties in conjunction with FEA or with conjunction with topology or conjunction with just design itself can help you get a much better product, much better part to use it for.
See if I can update these real quick. These are slightly out of date. So if you go back into Lab 4, you'll see that we've got all of the different parts there. There we go. And so what you'll do is you'll do a mass properties analysis on this assembly, and then you can change the parametrics that are in there to make it wider, taller, shorter, shallower. And so then using that information, you guys can see how much those mass properties will change. So for the homework, or excuse me, for the lab, you'll assign some material properties to these different parts. You'll go ahead and conduct a basic mass properties analysis, and then you can adjust the parametrics and rerun the mass properties to see what improvements were made. Okay, and then you'll capture a before and after image and insert these images into Google Doc, as well as include the information from the mass properties. So you'll do that for 1 and 2. You'll conduct the mass properties for the individual parts for part 1, and for part 2 you'll do the entire assembly. And then for the last one, this one's just the image of the improved suspension based on those mass properties. So you guys can just post that up there. As far as the homework, it's kind of the same thing, except you just do it with the parts from your vehicle. So it's pretty straightforward. And then just make sure that you follow the naming nomenclature, lab 11 _ your name, and then you can just add those images to your homework submissions. So that's all for lab 11. So hopefully that shouldn't take too much time for you guys. So for lab 10, we're going to be doing finite element analysis for assemblies. And so the point of this is to kind of see how the distributed loads will affect not only one part that you do an analysis on, but also see how those loads carry over to the other parts, which I think is probably a lot more important than the actual model itself. So I've put up a wheel rim and a shaft that goes through it. These are images from NX, but they're very similar to what we've got here in Catia. And so we're going to go ahead and kind of walk through this in-class exercise, showing you guys how to kind of glue these parts together, how to do an analysis, apply some loads, things like that. It's very similar to what we learned in the last lab. And then once we're done with that, you'll go ahead and apply those same techniques to the Lab 4 lower control arm, and then you'll just generate a PDF for those and you'll turn those in. For the homework, you'll apply these same FEA techniques to another subsystem of your vehicle. So you do need to make sure that you've got some subsystems in your car that you can actually do a finite element assembly analysis on. But then you'll go ahead and run that analysis, generate a PDF of that, and that will be what you'll turn in. So
Will we each need to do a separate subassembly?
for the vehicle, it would be nice because that way you can kind of throw those into your final presentation or your design reviews as you're going. But for this assignment, it doesn't have to be a different subassembly. So if you guys want to throw together, you know, the front wheel suspension really quick, that would be awesome because then you can also use that for the motion simulation, which we'll be covering next lap.
So ultimately, at the end of the semester, you want potentially one subassembly analysis per member. But for this, done in a week kind of thing, we're hoping that you can, as a group, throw something together, everybody work, and figure out how to do it on that one thing, get it turned in, and then just over the rest of the semester.
Okay. All right, guys, we're going to switch gears. I'm going to use a model that's a lot simpler that I know will work. So real quick.
Totally nuts.
So we're going to do a new part. Yeah, for the in-class assignment. And real quick, I will load this up to Google Docs, so you guys can do it, or you can just follow along. Either way is fine. You could probably build it. It should be pretty straightforward.
Angle, put a hole in it.
Let's see. Let's check our units real quick here. Let's make this in inches. It's 25. There we go. Just do like 25 inches long. Looks pretty good. Okay, and then let's put a hole in it. Let's do yeah, I did 25 in length. 25 in length. Let me check it real quick here. From here to here. Okay. Real quick, let's go into the first sketch and I can check that real quick. Let's do 2 wide. And do 1 thick. Okay. Let's come down here to the hole. Let's make that 0.5. And we'll have the hole go all the way through. Okay, there we go. So we've got a hole there at the end. Fairly straightforward. We're going to go ahead and save this off. Just a 1/2 inch diameter hole, and I constrained it there 1 inch away from the edge and 1 inch from either side, so it's right in the middle of the beam. I'm going to do a new part, and this one will be a shaft. Diameter of which will be 0.5, and we'll extrude or pad it up. Let's pad it up 10 inches. Save that off as shaft. Okay, and then we'll create a new product, and we will bring in the shaft. I made it 10 inches.